Hello and good evening, everyone. My name is Shraddhargo Mukherjee. In this channel, I will be teaching you chemistry. What we will do is we will first complete the chapters, have a clear understanding about the theories and the conceptual clarities of the chapter. Then, after that, as we proceed further, we will solve the questions. Which questions? The questions that came in previous years in the various competitive exams like JEE mains as well as Neet. At the end of the chapter, when we have the absolute conceptual clarity and we are very clear about the concept of the chapters, then we will solve few questions that has appeared in JEE Advance, right? So first of first things first what we need to do is we need to have our pen and paper ready. It's not a PDF form of lecture. It's like the old school board and paper. I will write on my whiteboard. You will take the running notes in your paper or copy, whatever it is. Make the running notes. If you come across any conceptual problem or if you have any doubts regarding the lecture, just put it in the comment section, and in the next lecture I will address those doubts. First we will clear the doubt and then we will proceed further. One thing I can assure you is if you go through the lectures with a calm mind and try to understand this lecture, you will have an absolute conceptual clarity about the chapter, and I can guarantee you that you will be able to solve the questions very effectively and in a very time bound manner. So, without further ado, let's start our lectures. The first chapter is coordination compounds. So, why this is the first chapter? It has been selected. I have selected this chapter. Actually, it's not been selected by anyone else. I have selected this chapter based on its importance. Every year, we see a bunch of questions from coordination compound in competitive exams like JEE Mains Neet. This is a very important chapter in inorganic chemistry, right? So, therefore, this chapter I think is very important. And since we are in the end of November and we have our first session of JE mains in the January, so I think first we will start off with this chapter and then we will move on to another part of inorganic chemistry. And probably, if I have time, I will simultaneously upload chapters for physical chemistry also. So, first things first, we are starting off with coordination compound. Put your pens and paper ready, have a clear mind, take a sip of water, and then we will start off with this chapter. Okay, so now let's jump in. So, coordination compounds. Okay, so why coordination compound? What are coordination compound? What is the importance of coordination compound? Everything will come along in this chapter, various concepts of coordination compound. So, first things first, these are, you need to know is these are complex compound. So what do you call it? We call it complex compound. Now, what do you mean by complex compound? See, we have always studied about simple compounds. Simple compounds as in various types of salts you have studied. For example, the basic ones NaCl, KCl. So these are formed of one cation Na plus and one anion Cl minus. Similarly, this one is formed of one cation K plus, another cation Cl minus. So these are simple salt, okay, or simple compounds. But this is a part of a complex compound. We call it as a molecular or addition compound. What we understand by this molecular or addition compound? Basically, these compounds are formed by addition. These compounds are formed by addition of two or more compounds. right? So basically, what we just told, these are not simple compound, but these are complex compound. Complex compound, these are basically called molecular or addition compound, right? Because these are formed by addition of two or more compound. So this molecular or addition compound, these are of two types. One is double salt. One is double salt, and the second one are coordination compound, which we will discuss in details in this chapter. First, what are double salts, right? Double salts, basically, these are formed by simple addition of two or more stable compound, formed by addition of two or more stable compounds. Stable compounds, and this has to be added in a stoichiometric ratio. This had to be added in a stoichiometric ratio. So, double salt formed by addition of two or more compounds, stable compounds, and they are added based on stoichiometric ratio. So, let's take an example of a double salt, right? If we take an example of a double salt, in DS I'm writing for double salt. So, let's say we have something like this. We have ferrous sulfate, FeSO4, plus we have ammonium sulfate, plus we have water. If we simply add these compounds, we will get a double salt, right? This is called more salt. Clear? So what we call, why it is falling under complex compound? Because you see there are two stable compounds. One is ferrous sulfate, one is ammonium sulfate. Both of them are salts, both of them are stable individually, and we have water molecules. So what we have, two stable salt just adding up to form a double salt. Similarly, if we take another example, let's say we have A2SO4, potassium sulfate, plus we have aluminium sulfate, plus again we have water. So if we add these things up, we will get this one, K2SO4 dot Al2SO4 whole 3 dot 24H2. This is the name of potash alum. So this is also an example of a double salt. So again, same logic. See, this is a stable compound. Potassium sulfate is a stable compound, can exist independently. Even aluminium sulfate is a stable compound, and we have water molecules. So all two stable compounds, two stable salt and a molecule, water molecule combines to form another compound. This is an example of a double salt, and this by far falls under molecular or addition compound. Now you can understand why the name addition compounds come, right? So this is an example of a one double salt, more salt. This is an example of an other double salt, that is potash alum. So now we are clear about double salt. Now let's move on to the another type, the type that we will be discussing more in this lecture, that is coordination compounds. So how this coordination compounds forms? So they are also addition compounds. So how this addition takes place? Let's say we have FeCN2, ferrocyanide, and in this we add excess KCN. We add excess KCN. So what we will get? We will get something like this. We will get a compound something like this, potassium ferrocyanide, right? So now again see the same logic. We have two individual compounds that can exist independently, ferrocyanide and KCN, potassium cyanide. They can both exist independently. Now they combine to form this kind of compound, which we call it as a coordination compound. Now you can understand this and say this. Of course, there is some difference with the double salt, right? In double salt, what we have done in double salt, we have write it in dot format, potassium sulfate dot aluminium sulfate dot 24H2. But this coordination compound, this potassium ferrocyanide that we have formed, this we have write in the form of a third bracket is there. So there must be some difference between a double salt and a coordination compound. So now, what is the difference? What is the difference between the double salt and coordination compound? Now the basic difference is whenever a double salt is dissolved in water, when a double salt is dissolved in water, what will happen is it will dissociate. It will dissociate into all the constituent atoms. So we will have, if this potash alum dissociate in water, if the potash alum dissociate in water, what will happen? We will get 2K plus 2 aluminium 3 plus 4 sulfate ion plus 24H2, right? So when a double salt dissociate in water, it gives all the constituent ions or molecules, right? So now let's say we have a double salt, we dissolved it in water, and now we are doing the individual test for potassium. So it will give a positive test for potassium. Again, if we are doing an individual test for aluminium, it will give a positive test for aluminium. If we are doing a test for sulfate group, it will give a positive test for sulfate group also, right? So now we know what is double salt doing in water. It breaks into all the constituent ions. Similarly, if we take this double salt also, when we put it in water, it will again dissociate into all the constituent ion. We will get Fe 2 plus we will get ammonium ion, 2 ammonium ion we will get, then we will get sulfate ion, plus we will get water. So again, if we do the individual test, for iron, we will get a positive test for iron. If we do the individual test for the ammonium group, we will get a positive test for ammonium group. And again, if we do a individual test for sulfate group, it will give a positive test for sulfate group, right? Now what happens in coordination compound? When a coordination compound breaks in water, what happens is it breaks down into 4K plus and we will have this entire group FeCN6 as a group. So this group that is inside the third bracket, this does not break, right? This group remain intact. It does not break when we dissolve it in water. So if we are doing a test, if we are doing a test for K plus, if we are doing a test for K plus, if we, then we will have a positive test for K plus because K plus is there in the solution. So we will get a test for K plus. But if we do an individual test for Fe plus in this coordination compound or Fe2 plus in this coordination compound, we won't get the test for Fe in this coordination compound because iron is not existing independently. Iron is combined with cyanide group, right? This part does not exist independently, so we does not get an individual test or we does not get this individual ions in the solution. Even if we do a test for individual cyanide group, let's say I want to see whether cyanide exists independently, again it will not give a test or it will not give a positive result for cyanide group. But if we do the complete test, if we do the complete test for ferrocyanide FeCN6 group, if we do the full test for this group, we will have a positive result. So what is the major difference between a double salt and a coordination compound? Double salt always breaks to all of its constituent ions. If potassium is there, we will get a test for potassium. If aluminium is there, so we will get a positive test for aluminium. If sulfate is there, we get a positive test for sulfate. So all the groups or ions present in the solution gives the positive test. But for coordination compound, the groups and ions that are present inside this third bracket, we call it coordination sphere. We will come to the terms after some times. But the thing that are present in the third bracket, they does not give the test for individual ions in normal scenario. Again, in normal scenario, okay. Then we will, after some time, we will again discuss. There are details of labile complex, inert complex, this or that. But for the time being, you need to know that the groups that are present inside the coordination sphere, they will not give the positive test for individual ion. Like here, if we do the test for Fe2 plus, no positive result will be there. If we do the test for Cn minus, no positive results will be there. But if we do the test for the overall group FeCN6, then we will get a positive test. So that is the basic difference between a coordination compound and a double salt. They both are complex compound. They both falls under the addition compounds also because they are formed by the addition of two or more compound, but one has a different property, another has a different property. In this chapter, we will mainly focus on the coordination compound. Double salt is there for the basic part, for giving you the general idea. But over here, that the topic we will discuss is coordination compound, and I think you have a clear idea about what coordination compounds are, right? Okay, let's move on. Now, before moving to the conceptual part, we have to know certain terms. We have to have an understanding about certain terms that are present in coordination chemistry. Before moving further, we should know, as we know, there are various terms like central metal ion, ligand. Previously, in few seconds back, I have mentioned something called coordination sphere. So we have to have a clear idea what this terms means in this. What are the uses of this? So the terms are something like this. The first term, that is the most important term, and you will be using this term a lot in this chapter. These are called the ligands. These are called ligands. Now, if you remember the coordinate bond, that is in chemical bonding, chapter 1, in class 11. So, if you just remember this, I will give you something, a basic idea if you just forgot it by any chance. What happens in a coordinate bond? Let's say we are taking an example of NH4 ion. This is formed by NH3 and then H plus, right? So first we will draw the ammonia molecule. Nitrogen has done its 3 bonding with the 3 hydrogen, but nitrogen has a lone pair, and we have a H plus ion. So H plus ion needs a duplet to complete its stability. So nitrogen will donate its electron, lone pair of electrons, to H plus ion, and we will have this NH4 ion. So this bond, these 3 are covalent bonds. These 3 that I have marked, that I'm marking with the green one, these 3 are covalent bonds. And this one, the donation of electron, this is called coordinate bond, right? And who is giving this electron? Ammonia is giving. So ammonia over here, NH3, will be called what? Donor atom, because it is donating an electron. Ammonia will be called a donor atom, right? Because the one that donates the electron, that is electronically rich atom, that is donating the electron to the electronically deficient ones, these are called donor atom, right? Donating. So basically, the ligands over here are the donor atoms. So basically, we can call it the donor atoms or molecules. Can be cation also, can be anion also. Donor atoms, molecules, cation, anions, which donates pair of electrons to the metal ion and forms a coordinate bond are called ligands. Okay, so what are the things that we knew? These are the donor atoms that donates a pair of electrons. So it can donate a pair of electrons. It can donate more also, but the basic is it has to donate one pair of electron. It can donate more also. We will discuss various types of ligand to the metal atom, to the metal ion, to where who is taking this electron? A metal ion is taking an electron, and the bond that is formed, that is a coordinate bond, right? So the bond that is formed is called a coordinate bond, and they are called, and the donor atoms, molecules, or ions are called ligands. Clear? Now the next is central metal ions or atoms. What are these? Central metal atoms. These are the metal atoms or ions which accepts the pair of electrons from ligands and gets attached are called central metal ions or atoms. So basically, ligands are giving a pair of electrons and the central metal ion are accepting a pair of electrons. They can accept one, more than one. So basically, the central metal atom accepts the electrons and the ligands donate the electrons. So first coordination compound we have studied or we have discussed is K4FeCN6. So over here, which one is ligand? This breaks down to K plus and FeCN6 4 minus. Now we are talking about this one, the part that is inside the coordination sphere. This part. Now over here, you can see this central metal atom. What is the metal present over here? Iron. This is the central metal ion. And this CN, the cyanides are the ligands. Right? So basically what it is doing, the iron is present in +2 state. So iron is accepting the ligand. Iron is accepting the electron pairs. Sorry, not the ligands. The iron is accepting the electron pairs from the ligands. So all these cyanide groups that are there, these are the ligands, and the iron that is present, that is the central metal atom or ions over here. Iron is in +2 state. So this is our central metal ion. And all this surrounding the central metal ion are the ligands. So we are clear about the true definition, the central metal ion and the ligands. Now moving on to the acid base concept. What we call when someone is donating a pair of electrons, which acid or which base they fall into. So someone which is a electron pair donor basically is a Lewis base. Electron pair donor is a Lewis base. So all the ligands that are donating the electrons, they are the Lewis base, and the electron pair acceptors are basically Lewis acid. So basically it's the acid base reaction in which the central metal ions are the Lewis acid which accepts the pair of electrons, and the ligands are the Lewis base that gives the pair of electrons, right? Okay. Now, seeing this, one thing that can come to your mind, can the ligand only donate a single pair of electrons, or is it possible for any ligand to donate maybe multiple pair of electrons? Who knows? So the answer is yes, it is possible for the ligand to donate more than one pair of electrons. So therefore, the next concept that comes is called denticity, right? So denticity is the next concept that comes, that depends, that basically describe, denticity basically describe the number of pair of electrons, basically number of pair of electrons donated by by a ligand. Now see, if you are in a biology student, or if you studied biology in class 10, you have come across this term of denticity. Denticity mainly means the teeth, right? So basically what is happening is, this ligands, they actually hold on to the metal by biting the metal. Okay. Now if a ligand is donating a single pair of electrons, it is biting in one end. If it has moved, so it can bite from two end also, or three end, or four end. So denticity mainly means the number of pair of electron that is donating by the ligand. So it has, it can coordinate with the metal ions. So by example you will see that, let's say there are monodentate ligands. What do we mean by mono? Very easy. Mono means one. Okay. So mono means basically one. Dentate means it is giving a pair of electrons. So how many pair of electrons this monodentate ligands can give? They can give only one pair of electrons. Right. We can have some example. Water molecule have a lone pair of oxygen, it can give. Similarly, ammonia, nitrogen has a lone pair, it can give. Similarly, we have something like this, what do you call it? Cn minus. Again, the negative charge can be given. So these two are neutral. These two are neutral ligands. This is an anionic ligand. Because it has a negative charge, it's an anion, so therefore this is an anionic ligand. So basically, if a ligand can donate only a single pair of electrons, only a single pair of electron, then it falls under the category of monodentate ligand. Okay. The next one, again, if we have one, then we will have two, so that is called bidentate ligands. Okay. So the first example, NH2, CH2, CH2, NH2. See, now there are two NH2 groups. Both have nitrogen, both have a lone pair. So this lone pair can be donated, of course, and this lone pair will also be donated. So this ligand is combining with the metal with two ends. So it has two teeth to grab on. If previously, if this was the metal, one ligand is connecting like this. Then this one, it has two teeth, so it is grabbing the metal something like this. So therefore they are called bidentate ligand. So again, this one is called, this name is ethylene diamine. Similar example, let's say we have this O minus can grab the metal by this end. This O minus can also grab the metal on this end. So again, two teeths. This is called oxalato, right? So these are bidentate ligand. These are the examples of bidentate ligand. These have two binding sides. They are grabbing the metal from two ends. Okay. Now, of course, there is a tridentate ligand also. Something like this. NH2, CH2, CH2, NH2, sorry, NH, CH2, CH2, NH2. Now three nitrogen atoms have three lone pairs. So it can combine with the metal using three ends. This one, and this one. So this is an example of a tridentate ligand. It is connecting with three sides. The metal is over here. It has three sides and it is attacking the metal from three sides, attaching with it from three sides. So it's a tridentate ligand. Basically, ethylene triamine. The name is ethylene triamine. Okay. Now the thing is, monodentate and bidentate we study individually, and after bidentate, so tridentate, tetradentate, pentadentate, hexadentate, we just give a common name. We call them as polydentate ligand. Clear? If the denticity is more than 2, if denticity is more than 2, we just generally classify them as polydentate ligand, because the important ligands are monodentate, bidentate, then we have something like ambidentate ligand also, flexidentate ligand also. So whatever it is, if the denticity is more than 2, we just generalize them as a polydentate ligand. Okay. For example, if someone has lakhs of money, we just call him lakpati. If someone has crore money, we call it crorepati. And then if we have more than money, so million, billions of dollars, we just give the general thing as it's they are rich. We don't know. We don't want to get into the details of this. Okay, so generalized, monodentate, bidentate important. More than them, if a ligand has more denticity than that, exactly possible, very possible, and then we give him a general term as polydentate ligand. Now, one of such ligand is ethylene diamine tetraacetate. What I just tell you is a ligand is there. The name is ethylene diamine tetraacetate. So first we call it EDTA 4 minus. What does this ligand look like? See, first we draw the ethylene diamine. If you remember it, it is NH2, CH2, CH2, NH2. This is our ethylene diamine, right? So what we will do is we remove the hydrogen. from the terminal amines. See, now tetraacetate means 4 acetate group has to be there. So as we have removed it, we will add the acetate group. We will, sorry, this is one acetate group. This is another acetate group. This is another acetate group. This is another acetate group. Okay. Both the nitrogen has the lone pair also. So it can combine in how many ways? It can combine through this oxygen. It can combine through this oxygen. It can combine with this oxygen, O minus, this oxygen, O minus. It can combine with nitrogen, lone pair. This can combine with this nitrogen. So how many denticities are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. So this is an example of a hexadentate ligand. Hexa means 6, hexadentate ligand. Now see, it is not necessary that EDTA will be using all 6. There are many complexes. There are many complexes in which EDTA is using 4 ligands. It is not using the 2 nitrogen lone pairs. It is only combining with the 4 oxygen atom. Okay, 4 O minus it is combining. So when the ligand has a choice, to not use all of its denticity, it has the capacity of 6 dentate. It can combine with the 6 dentate point, but it is choosing not to combine with the 6 dentate. Instead, it is using only 4. The requirement is 4. So, this type of ligands are also called flexidentate ligand. Flexidentate ligands. When the ligand is flexible in nature, it comes from flexible. It has 6 using 4. Maybe some ligand has 5 using 2. Just a random example. So this ethylene diamine is both a hexadentate ligand as well as a flexidentate ligand. Okay. So it is using any one of them. It's not using all of them. It is using some of its binding site. Then it is a flexidentate ligand. These kind of things are important in JE Advanced when there are multiple options correct, right? They will give you EDTA is a hexadentate ligand, a flexidentate ligand, a ambidentate ligand, none of these or all of this, whatever it is. So ambidentate we have not studied yet, but over here both the options will be correct. It is hexadentate also, it is flexidentate also. Now the thing, the ligand that we will study is a type of ligand called the ambidentate ligand. This is an important one. Look at ambidentate ligand. Ambidentate ligands are ligands containing more than one coordinating atom. What do we mean by this? See this. There is a metal and there is a nitro group in double bond O, O minus. Nitrogen has a lone pair. It can combine with the lone pair. Okay. Similarly, again the nitro group, metal is there, oxygen O minus is there, N double bond O. It can combine with the negative charge also. So the basic difference is it has two atoms that can use for combination. So it has basically more than one atom, more than one coordinating atom. Over here, what are the coordinating atom? One is nitrogen, one is O minus of oxygen. So both are nitro groups. Basically the group is NO2 minus. Both are nitro groups, but in the first one, nitrogen is acting as a binding center. The second one, oxygen is acting as a binding center. Now understand this. These are ambidentate ligand. Okay, this is not flexidentate. Flexidentate means what? You have multiple and you are using some, not using the rest. But in this ambidentate, you can use only one. Either you go with nitrogen or you go with oxygen. Okay, let's say for example, in a flexidentate ligand, let's say you have 6 cars. Okay, and now to move from place A to place B, all of your family is traveling, so you can either accommodate your family by sharing and using 4 cars only. Okay, that is possible. Or let's say individually each member is driving 1 car, so you can use 6 car also. So this is a choice you have. Okay, next thing is you have to go one place to other. You are traveling, only you are traveling, and you have a car and you have a bike. You have a bike, right? So basically this is a bike. Don't mind my drawing. My normal drawing is pathetic, but chemistry drawing is okay. You don't have to worry about that. So now you have only one binding site. See, only you are traveling. Previously, all of your family members are traveling. So you can have a sharing thing also. Over here, there are 6 binding sites. You can use only 4. So now there is a chance for a flexidentate. Okay, you can adjust 2 members in 1 car and then move on with the 4 cars. Okay, that is possible. But over here now, you are going to the market, you're going to any kind of bazaar or whatever it is, and you have option either you can take your car or you can take your bike. You can't take both. You can't drive two at the same time, right? So this is a basic difference between a flexidentate and an ambidentate ligand. ठीक है, ambidentate ligand में क्या होता है, एक ही बाइंडिंग साइट है, एक ही बाइंडिंग साइट है, either you can use nitrogen or you can use oxygen. Over here क्या है, over here what is happening, यहाँ पे 6 बाइंडिंग साइट्स और मुझे नेसेसिटी है 4. So now I am using 4 out of 6, so that is okay, fine, चलता है क्योंकि मोर देन वन है, सो यू कैन यूज दिस. बट यहाँ पे एक ही बाइंडिंग साइट्स है. सो दिस इज अ बेसिक डिफरेंस बिटवीन एम्बिडेंटेड लिगेंड एंड फ्लेक्सीडेंटेड लिगेंड. Now, next day, what we will do is next lecture, not the next day. Next lecture, I will give you the list of all the ligands and their name, because nomenclature is there in this chapter. Means the coordination compounds are named in a particular fashion, right? So before moving on to the nomenclature, we have to know the oxidation state of the metal, how we can calculate oxidation state. But first and foremost, we need to know the name of the ligands. Name थोड़े different है. They are a bit different from other ones. For example, in chemistry, we have studied that NH3 is called ammonia, right? It is called ammonia. When it is a ligand, we call it amine. H2O normal, from class 2 we are studying it is water, but when it is ligand it is called aqua. So based on this, there are various ligand, it has various name. You have to memorize the name because nomenclature karna hai. It's every year in JEE means 2 or 3 sets there will be nomenclatures. So that we will be doing. First thing that we will doing is various types of ligand that are there. Then we will see various other terms. Central metal atom we have done, how to find the oxidation number, how to find the coordination number, what are coordination number, what is coordination sphere, what is ionic sphere. These are the things. Homoleptic complex, heteroleptic complex, there are various terms. So next class will also be a theoretical class, mostly remembering base. And then at the end uh, of second class, and we will move on to the third lecture we will jump to the nomenclature part. Now you might think that why so much remembering, you have to memorize quite a lot, right? So now see, in inorganic chemistry, that is the advantageous part. Initially it is a bit problematic that you have to memorize some part and do this something, but once you have memorized it, it became very less time consuming as compared to the physical chemistry where you have to solve the numericals. So there is a dicey situation. But in inorganic and organic chemistry, if you know the concepts, okay, it will save you time. These two part, particularly if you are giving JE mains, in Neet biology has its advantage that it's also a time saving part. If you know the answer, it will save you time. But if you're giving JE mains, only organic chemistry and inorganic chemistry are the two subjects, along with modern physics, that will save you time for the numericals. Okay, the time you save over here, you can use it in the future in this exam to solve the numerical problems. May it be physics numericals, may it be chemistry, physical chemistry numericals, may it be mathematics numericals. But these part, this inorganic chemistry and this organic chemistry, this will buy you time. Therefore, these chapters are very important, right? First, there is a very low chance to make errors, very less chance, because if you have the conceptual clarity, the questions you will solve. It's not that difficult. So that is one advantage, and second advantage is your time. So for this two reasons, these parts became very important. So I hope I will see you in the next lecture. I hope you have understood this. If you have any doubt, feel free to put it in the comment section. And in the next class, again in a schedule, every day I will be uploading one lecture. So maybe this will take a total of 10 to 15 lecture based on how many number of questions we do. By 15 lectures, we will be completing the full chapters in a very holistic way. Okay. So that's all for today. Have a nice day. Study hard, study conceptually, remember stuff, but understand the concepts also. And we will see you in the next class. Bye bye. Have a good night.